Every second, planets are racing around the sun at incredible speeds, some moving at tens of thousands of kilometers per hour. But here's the weird part: the paths follow precise rules that were figured out 400 years ago. So let's dive into Kepler's three laws to unlock those secrets. And the first of the three is the law of orbits, that simply states that all planets trace elliptical paths with the sun as the focus. So consider this planet that moves in an orbit around the sun. Then this orbital shape is what we call an ellipse. So imagine you want to draw a circle on a board. You simply fix a pin at the center, tie a string to it, attach a pencil to the other end, and move it around. The pencil traces out a perfect circle. Now, to draw an ellipse, you need to place two pins instead of one. Tie the ends of a string to these two pins, keep the string taut with a pencil, and then move the pencil around while keeping the string stretched. The path traced by the pencil is an ellipse, and these 2 points are called the focal points of the ellipse. And here you can see that the sun sits at one of the focal points of the ellipse, although many people mistakenly think that the sun sits at the center of the orbit. Now here comes a bit of geometry, which I think is quite straightforward. So this orbit, an ellipse, has what we call a semimajor axis A and eccentricity E. Now what exactly is eccentricity E? So E is a dimensionless number between 0 and 1, and for a given ellipse, its value is such that if you multiply it with A, the product EA becomes the distance between the center of the ellipse to point F or F dash. So if eccentricity E is 0, you see these distances will become 0 and the two foci would collapse towards a single point, that is this, and what you get is a circle. So lower the eccentricity, that is closer to 0, more it will look like a circle. And you can see if the eccentricity moves towards 1, what you get is a very elongated ellipse. Another interesting thing to know about the geometry of ellipse is that the sum of the distances from F to the planet and from F dash to the planet is the same for all points on the curve. That is, if you sum up, let us say, these distances, then it would be the same in value as summing up these distances or any other point on the ellipse. And this constant sum is what makes ellipse unique and is a very property that allows planets to follow predictable paths. So you see, the first law is quite simple, but it is important to understand the geometry around it. So the second law is called the law of areas, and I find this the most interesting of the three laws. And it says that if you connect the planet to the sun with a straight line, then this line will sweep out equal areas in the plane of the planet's orbit in equal time intervals. So if the planet moved from here to here in time delta t, and say here it moved from this point to this point in the same time delta t, then these two areas would be equal. That is, delta A upon delta t is a constant, or in differential form, the rate dA upon dt at which the line sweeps out the area would also be a constant. Now, if you were to interpret the physical meaning of this law, it is quite fascinating. That is, the planet moves slowest when it is farthest from the sun and speeds up as it gets closer. Because you see, if here, let us say the planet moves through this arc and sweeps a certain area, then to sweep the same area over here, it'll have to move a longer arc and therefore speed up. And here's the interesting part. This law isn't just about orbits. It actually connects to the deeper principle of physics, that is a conservation of angular momentum. So let me walk you through how the two connect. Well, you see, the area of this triangle, you could say, is almost equal to the area swept in time, delta t, by the line connecting planet and the sun. Now, simple geometry tells us that the base of this triangle is r delta theta and its height is r. Then, using the formula for the area of triangle, which is half into base into height, we get delta A is equal to half r delta theta times r, which equals half r squared delta theta. And you can visualize that this expression for area delta A will become more accurate as delta t approaches 0. Because delta theta also approaches 0, making this base more and more aligned with the actual arc or trajectory of the orbit. Okay, now if we differentiate this equation with respect to time, we can find the instantaneous rate at which the area is getting swept out. That is, dA upon dt is equal to half r squared d theta upon dt, which equals half r square omega. So here omega is nothing but the angular speed of the line connecting the sun and the planet as it rotates around the sun. Now, let us consider the linear momentum p of the planet at this point, and also its two components, radial and perpendicular. And we know that L, or the angular momentum, can be written as a product of r and perpendicular component, that is this. That then equals r times mv perpendicular. Then we can write v perpendicular as omega r. So this equals mr square omega, or r square omega equals L upon m. Now, if we put this expression for r square omega here, what we get is dA upon dt is equal to L upon 2m, or L is equal to 2m times dA upon dt. But we have concluded earlier that dA upon dt is constant, which therefore means that here L should also be constant. That means the angular momentum of the planet is conserved. So in simpler terms, what Kepler discovered here is really a reflection of the law of conservation of angular momentum at work. This explains why comets and planets speed up near the sun and slow down when farther away. Not just a coincidence, but a deep physical law in action. Okay, let us move on to the third law, that is called the law of periods, that says that the square of the period of any planet, that is the time it takes to go around the sun once, is proportional to the cube of the semimajor axis of its orbit, or t square is directly proportional to r cube. Like always, it is a good idea to derive this for better understanding. So let us say the mean distance between the sun and this planet is radius r of a circle. And it may be worth noting here that most planetary orbits are close to a circle, which means the E value, or the eccentricity, is close to 0. As an example, Earth itself has an E value of 0.017 and Venus as low as 0.007, making both close to perfect circular orbits. In contrast, comets can have eccentricities close to 1, making the orbits very, very elongated. So earlier we took an exaggerated ellipse basically to understand the concept around ellipses. So with this new piece of information, that is the planetary orbits are almost circles, we will apply Newton's second law to an orbiting planet. And what we have here is gmm upon r square, which is a force, equals m times omega square r. Then putting 2 pi upon t for omega, where t is the time period of the planet's motion, we get t square is equal to 4 pi square upon gm times r cube. And you can see this part is a constant depending only on the mass of the body at the center around which the planets are orbiting. So we get the proportionality between the square of t and the cube of average radius. And this equation holds very much for elliptical orbits also if we replace r with a or the semimajor axis. Again, the physical interpretation of this law is that it predicts that the ratio t square upon r cube has pretty much the same value for every planetary orbit around the Sun or any other massive body. So for our solar system, Earth's average distance from the Sun is about 1 astronomical unit and its orbital period is 1 year. Plugging these values gives t square upon a cube is equal to 1. Now, if we take another planet in our solar system, say Mars, for which a is 1.524 AU and t is equal to 1.88 years, what you get is t square upon a cube is again 1. And this ratio of 1 would be true for all planets in our solar system. Now, if you were to take some other planetary system with a different star instead of the Sun, the value of this ratio would be different. But for all the planets in that planetary system, it'll be the same. So a great example is a TRAPPIST-1 system that has a value of 11 for this ratio. And it arises from the fact that the star TRAPPIST-1 has a different mass than our Sun. So when you look up at the night sky, remember, those distant points of light aren't just drifting aimlessly. They're moving with absolute precision, bound by invisible rules that Kepler uncovered centuries ago. And who knows, perhaps one day it'll be you using these same laws to plot the course of spacecraft across the stars. So if you like the lesson, give it a thumbs up, that'll be helpful. And if you want the complete list of lessons on gravitation, check out this playlist and I will see you in the next lesson.